Welcome to my presentation. In this presentation, let us look at some applications related to vectors in 3 dimensions. In particular, let us try to find the area of a parallelogram if the sides of the parallelogram are given to us in terms of vectors. Let us say the vector A is given to us as 2, -1, 0, and then we can express this as components of vectors as 2i minus j plus 0k, and then let us say vector B is given to us as -1, 2 and 0, and the way we can represent that in terms of components is negative i plus 2j plus 0k. And just for our understanding sake, I want to plot the graph, plot these two vectors on the graph. I've got the graph started so that we don't waste time, and I wanted to get that going, and I can point it out as we talk. So vector A is 2 units on the positive x-axis. So from the origin we go to travel 2 units on the positive x-axis, 1 unit on the negative x-axis, so we go left 1 unit, and then 0 units on the positive k-axis. So there is no height there, so we're going to just leave it there. So I have represented that with a green line starting from the origin and ending at that point, and this green line here is vector A, which has 2i minus j plus 0k as components. Vector B can be represented as the other side of the parallelogram, and then the components of those are given to us as -i plus 2j plus 0k, and I've plotted it out on the graph here. So that means we are traveling -1 unit on the negative x-axis, going the other way, and then 2 units on the positive x-axis, so on the positive y-axis, so we went right side 2 units, and then 0k, that means we don't have any height there, so those are the 2 units we have. And I put a small circle, a red circle around there, and then I've joined it with a green line starting from the origin to that point, and I've indicated that as vector B, and vector B is -i plus 2j plus 0k. Now it is just a matter of completing the other sides of this parallelogram. It appears that if I were to take the terminal point of vector A and then draw a parallel line to vector B, it's going to look something like this. It's going to look like that. I'm going to draw that with a red line like that. And then if I were to start from the terminal point of vector B and draw a parallel line to vector A, that is how it's going to look like. So now we have a parallelogram, and we want to find the area of the parallelogram. The area is this hatched region inside this, which is indicated by these blue lines, is that hatched region which we want, and we want to find the area of that. This parallelogram looks very similar to this here. If I were to draw it out in this manner, this is vector A, and this is vector B, and we want to find the area of this parallelogram, and we want to use our vectors properties to do that. And to do that, we're going to write it out in this manner. We know that the area of the parallelogram, the area of a parallelogram is given to us as vector A cross vector B, and we're going to take the magnitude of that, and that should give us the area of the parallelogram. To do that, let us write them down in these different steps. Step number 1. We'll first find the cross product between vector A and vector B, and then we'll try to find the magnitude of that in step number 2. So vector A has 2I minus j plus 0k as its components, and we're going to cross multiply that by the vector v, which is I negative I plus 2j plus 0k, like that. Therefore, we will use the determinants procedure to simplify this. We're going to write I, j, k as the first row of the determinant, and in the second row and the third row we will write the coefficients of I, j, and k for vectors a and b. So the coefficients of I for vector a are 2, the coefficients of j is -1, the coefficient of k is 0. The coefficients of I for vector b is -1, the coefficient of j is 2, and the coefficient of k is 0. We will find the determinants by expanding the minors, and therefore we will travel along the first row, and then the sign convention we're going to use is positive, negative, positive, and therefore when we expand this, it's going to be as follows. I, the minor of that is -1, 0, 2, and 0, minus j times the minor of that, which is 2, 0, -1, 0, and then plus k, the minor of that, which is 2, -1, -1, and 2. So when we expand this, we're going to write this one out as follows. I times -1 times 0 is 0, 2 times 0 is 0, minus j times 2 times 0 is 0, minus 1 times 0 is 0, plus k times 2 times 2 is 4, and -1 times -1 is +1 minus 1. Therefore, that is how we can write that. Therefore, this, when we simplify, it is going to be 0i plus 0j, 4 minus 1 is 3, therefore 3k. So that is what we have. This is vector A cross vector B. What we need to do now is find the magnitude of this, and that will give us the area of the parallelogram. So the magnitude of A cross B, we can write this as follows, and therefore we are going to take the components of A cross B, which are 0, 0, and 3, and raise them to the power under this radical sign. 0 raised to the power of 2, 0 raised to the power of 2, 3 raised to the power of 2. So when we simplify this, this is going to be 0 plus 0 plus 9 under the radical term. Therefore, this is going to be square root of 9. Therefore, 9 is a perfect square. Therefore, the value comes out as 3. Therefore, the area of this parallelogram is 3 square units. 3 square units, depending upon whatever units the sides take on. If it takes on meters, it is going to be 3 square meters. If the sides of the parallelogram are in inches, this is going to be 3 square inches, and so on. This is the way we can find the area of geometric figures using vectors in 3 dimensions, using the determinants, using all of the information which we have learned up till this point of time. In my next presentation, we shall look at some more examples related to applications of vectors in 3 dimensions.